In this video, we introduce cross-validation, one of the most important ideas in machine learning. We focus on the conceptual and mathematical aspects. We'll describe how to implement cross-validation in later videos. To motivate the concept, we will use the two-digit data presented earlier. We introduce, for the first time, an actual machine learning algorithm, k-nearest neighbors. Let's start by loading the data and showing a plot of the predictors with the outcome represented with color. We can do it using this code. We will use these data to estimate the conditional probability function as previously defined, this equation. With k-nearest neighbors, we estimate p of x1 and x2 in a similar way to bin smoothing. However, as we will see, k and n is easier to adapt to multiple dimensions. First, we define the distance between all observations based on the features. Then, for any points x1 and x2 for which we want to estimate p of x1, x2, we look for the k nearest points to x1, x2, and then take an average of the zeros and ones associated with these points. We refer to the set of points used to compute this average as the neighborhood. Due to the connection we described earlier between conditional expectation and conditional probabilities, this gives us an estimate of px1, x2, just like bin smoother gave us an estimate of a trend. As with bin smoothers, we can control the flexibility of our estimate, in this case through the k parameter. Larger k's result in smoother estimates, while smaller k's result in more flexible and more wiggly estimates. To implement the algorithm, we can use the knn3 function from the caret package. Looking at the help file for this package, we see that we can call it in one of two ways. We will use the first, in which we specify a formula and a data frame. The data frame contains all the data to be used. The formula has the following form. Therefore, we would type y tilde x1 plus x2, like this. If we're going to use all the predictors, we can actually use a dot like this. So the final call will look like this. For this function, we also need to pick a parameter, the number of neighbors to include. Let's start by estimating the function with the default k equals 5. In this case, since our dataset is balanced and we care just as much about sensitivity as we do about specificity, we will use accuracy to quantify performance. The predict function for k and n produces a probability for each class. We keep the probabilities of being a 7 as the estimate of p hat x1, x2. You can get it like this. We also see, by using the confusion matrix function, that we get an accuracy of 81 to 82%. Previously, we used linear regression to generate an estimate for this same dataset. The accuracy there was 75%. We see that k and n, with just the default parameter, already beats regression. To see why this is the case, we plot the estimates p hat x1, x2 and compare it to the true conditional probability p of x1, x2. We see that k and n better adapts to the nonlinear shape of p x1, x2. However, our estimate has some islands of blue in the red areas, which intuitively does not make sense. This is due to what we call overtraining. Overtraining is the reason that we have higher accuracy in the training set compared to the test set. We can see that with k and n, overtraining is at its worst when we set k equal to 1. With k equal to 1, the estimate for each x1, x2 in the training set is obtained with just the y corresponding to that point. In this case, if the x1, x2 are unique, we will obtain perfect accuracy in the training set because each point is used to predict itself. Remember that if the predictors are not unique and we have different outcomes for at least one set of predictors, then it is impossible to predict perfectly. Here we fit a k and n model with k equals 1. Notice that the accuracy on the training set is over 99%. However, the tested accuracy is actually worse than regression. We get 74%. We can see the overtraining problem by plotting the estimates. You can see them here. The black curve denotes the decision rule boundaries. The estimate p hat x1, x2 follows the training data too closely. You can see that in the training set, boundaries have been drawn to perfectly surround each single red point in a sea of blue. Because most points x1, x2 are unique, the prediction is either 1 or 0, and the prediction for that point is the associated label. However, once we introduce the test set, we see that many of these small islands now have the opposite color, and we end up making several incorrect predictions. Although not as bad with this example we just saw, earlier we saw that with k equals 5, we also have some overtraining. Hence, we should consider larger values of k. Let's try, as an example, a much larger number. Let's set it to 401. With this, we get an accuracy in the test set of 79%. It turns out that this is similar to regression. We can see it by comparing the estimates of px1, x2 with the two models. This is because the size of k is so large that it does not permit enough flexibility. We call this oversmoothing. So, how do we pick k? In principle, we want to pick the k that maximizes accuracy or minimizes the expected MSE as we defined earlier. The goal of cross-validation is to estimate these quantities for any given algorithm and any set of tuning parameters such as k.